So it's 9:15. Let's get started to just be on time regarding the planning. Welcome to this 2022 edition of the SOFA Week. Today is the second day actually of the week. Since yesterday there was already a training session. So it's the international symposium, the occasion basically for research teams, independent developers, and companies to present what they are up to and what they did in the last years in terms of scientific and technical progress and achievements. Thanks a lot for attending. We're a few here in the room. We were actually all located in the same city, and you're like about 40 and maybe more now online. I'm going to say that again, but more than 200 to be registered for today, so that's nice. We studied, that's more or less always the same organization for the SOFA Week. We start with a training session that was actually yesterday on Monday 14th. And then it continues with the symposium, the day, so today is with the scientific and technical presentations from the community. And we end the week, and it's going to be starting tomorrow, the technical committee, which aims at really presenting what occurred on the technical point within SOFA, what are the evolutions within SOFA, what are the new plugins and so on, and what will be the next development task for the next 6 months. That's in order to design the roadmaps. That's for the technical committee. So about today, so it's the symposium, as I said, and I'll do a very short introduction about SOFA for those who maybe just got started or are curious about SOFA and got connected for today. SOFA, it's an open source project that started back in 2006. Maybe I guess here in the room, most of you know that, but maybe not in the crowd. It started since the very beginning from the need of several research teams to share a common collaborative framework for physics simulations. Physics simulation for medical simulation for some of them, for computer graphics for some others. So it was already for different purposes, but the need to actually share a common tool, a common simulation framework. And today, SOFA aims at being the open source reference for interactive and real-time application. As I said yesterday in the training, the keyword of SOFA, and I guess if you got sometime the question of why SOFA rather than other solutions, I think the most important point of SOFA is really the interactivity, the aim to have simulations where a user can interact with, where an optimization can actually interact with as well, or trigger SOFA simulations. And more recently, there is a lot of AI applications connected to SOFA as well. So the interactivity is definitely the keywords of SOFA. SOFA, it's a physics engine, so it's mimicking physics, the physics around us, especially the physics in the human body. For historical reasons, people are using a lot the soft and rigid body dynamics algorithms for modeling the human body, but not only for medical simulation more recently, and that's going to be the case for today. Today we're going to have also a lot of robotics, medical robotics and soft robotics applications with SOFA. Since the beginning, SOFA is following a concept. I mean, some of you were there maybe at this beginning. I wasn't, but the concept has been pursued, the idea to have a flexible framework that allows to easily design a simulation, a scene file, whether it's in XML or today in Python, to have a code, a framework, a software which is modular so that we can activate or deactivate features. And in order to be interactive, as I said, whether it's for user interaction, optimization, or whatever, the need of efficiency. So that's the purpose that we are actually following and the concept we are actually following with SOFA. What you will actually find, sorry, on the GitHub account of SOFA, github.com, SOFA framework/SOFA, it's mostly actually C++ code under a license which is LGPL, and for those who are again new to SOFA or new to open source, meaning that you can download, use it, modify it, and make product based on SOFA. The idea behind the license LGPL is really to get contributions back on the core of the framework of the software here on the SOFA core, so that the core improves on an everyday basis while being shared by all the participants, whether it's industrial or academic partners. We have Python bindings. I just mentioned that here, you know, the SOFA Python 3 plugin that now I guess most of you guys know. And around this core, anyone, and that's actually the philosophy of the idea behind the logo, is that we have a core, and all around there is plugins that anyone can develop under a license which is free to define to the developer and its institution. The way we are working on an everyday basis with SOFA, it's using a versioning system, which is Git. And the idea is to have a clear, simple way to contribute while having always this review process, which actually bring robustness to the project. So that's the way actually many projects are working, and on GitHub, all projects are working this way. If you have questions about that, do not hesitate to use, like here, you have a small GitHub discussions. It's a forum for asking any kind of questions you may have on SOFA, for asking for help or whatever. So do not hesitate to use it, and obviously do not hesitate to contribute to SOFA. All those contributions, they are actually discussed every week, during the week, and especially on the weekly dev meetings, which is discussing all the everyday evolution on SOFA. So again, do not hesitate to share yourself the fixes, whether it's in a small plugin hidden somewhere, or if you are improving the codes within SOFA, never hesitate to share your contributions. The release of SOFA, the latest one, is the one from June, so the 2206, and obviously a new one should come very soon, the 2212, and this results actually from the technical committee, which is giving like the roadmap for reaching this next release. A word about the community. So for 16 years, we have been working with SOFA and developing SOFA. It brought like many collaborations between academic partners, and not only. Now we have like startups, companies, and independent developers around the project. And good too. So yeah, the color map is actually not perfectly up to date. As I said during the training, Chile is missing, Belgium is missing, Netherlands is missing. So a few countries are still missing. If yours is actually missing, let me know. I would be happy to update it for the next events. And the crowd of today, so it's more than 200 registered participants, and so far from what I looked like over the weekend, it was more than it was exactly 30 different countries. So that's again a slight improvement compared to last year. For this morning's schedule, that's what we have at the menu here. First, we're going to talk about both biomechanics and medical simulation, and we're going to have another session later on this afternoon. And soft robotics, as I said, which is another trendy topic currently. So soft robotics, and it will be for both sessions a session with 4 presentations. Each of the speakers will make the presentation. There will be some time for questions right after, like 1 or 2 questions. And once the 4 presenters have made their presentation, there will be a 20-minute break. And this 20-minute break can be either used to take a coffee, if you'd like to take a coffee, or obviously to join us in some sub-rooms. It's called breakout rooms here in the interface. And you may actually join those breakout rooms, so that you can actually directly get in touch with the presenter, ask any question you want, and it will be like in a smaller committee compared to the main stage. After the 20 minutes, we'll get back to the main room here where we are, and the next session will start. Obviously, we may keep some breakout rooms open for people if they want to chat privately a few minutes more, but we're always going to have this opening breakout rooms, closing them once you've discussed during the 20 minutes with the speakers. We're going to have a bit more than an hour break for lunch, and we're going to have then the afternoon session that I'm going to mention right afterwards. To join one or the other breakout session, you just here in the interface go in. Once it will be open at the end of the 4 presentations. You go in participants. Then you'll have this breakout session appearing, and you'll be able then to choose and join any of the session you'd like, depending on the presenter you wanna ask a question. No worries. Once you are in the breakout session, if you leave here, you're not leaving the whole conference. You're just leaving the breakout session and getting back to the main room. You should have a polling soon, appearing here in the interface. If you want to answer this polling, it will be just random questions about your use of SOFA, so do not hesitate to answer it. And that's for the afternoon, but I'll get back to that, with a session about numerical methods and AI, soft robotics again, and biomechanics and medical simulation. Again, that's part 2 for those 2 sessions. At the end of the day, we're going to have the award ceremony. The idea is that every year we try to celebrate the best contributions of the year. And there's 2 prizes. First, the organizers' prizes, or I should say the jury prizes. We set up a jury every year, made of various people from the community. I will mention them afterwards. They elect according to their mind the best contribution, but you will also be able actually to vote. There is a public prize. And I will present all the contribution at 1:15 earlier in the early afternoon. You can already vote here online. The link here is already working. So sofaframework.org/sw22/vote. If it does not work, let me know. I would fix that over the first break. And here you'll be able to vote for the contribution you actually do prefer. So we're going to start now the first session. I think you can come here on stage. So there will be a few presentations made by people here in the room. As I said, we're about 10-15 here, people located in Strasbourg, very close to Strasbourg. And there will be, most of you are actually online. And again, thanks to you for joining this actually mostly online, but a bit hybrid event here. We're going to open this first session about biomechanics and medical simulation. The first speaker will be Vladimir, talking about cutting. That's a hot topic for many of you. Then Professor Choi from South Korea will present their work and their product on vascular intervention assistance robot. François, who is here in the room, will present a work that has been done by Insimo and some research partners on the knot identification and for robotic suturing, actually with Lille also, which is here. And we'll conclude with the work of Arnaud from University Luxembourg on Sonics, which is a coupling between SOFA and Phoenix, and he will tell you more about that. Again, we're going to have those 4 presentations, 1 or 2 questions at the end of each presentation, and then 20 minutes for asking all the questions you want to each of the speakers. And that will be room number 1 for Vlad, room number 2 for Professor Choi, room number 3 for us actually here. So yeah, for François and Lille, and room number 4 for Arnaud. So that's going to be it. All right, we're going to get started with you, Vlad. You can actually share your screen.
I think I'm sharing actually. Did you transfer the rights?
I was taking.
If it doesn't, I'll just restart.
There. Does it work?
No. I'll just restart.
Yeah, we're gonna get restarted here. If there is any question, obviously do not hesitate to just post it in the chat. We'll be happy to transfer it.
I think it's working now. Okay, so good morning, everyone. Welcome to the presentation about interactive cutting in SOFA. That is a small plugin that I've been working on for the past few months. I'll first briefly talk about the motivation, what I wanted to achieve with this plugin, then talk about the actual pipeline, how we do that, how we perform cuts in SOFA. And finally, I'll talk about integration with philosophy. That's yet another framework that integrates SOFA with a PBR renderer called Filament. And finally, I'll briefly discuss the future work that is planned. So basically, at the moment, tissue cutting is one of the typical procedures that you perform in any kind of surgical simulation. But unfortunately, I was not able to find any plugin that is open source available for SOFA. So with that, I set off to find the good way, the best way for me to implement cutting in SOFA. And I set several tasks. First of all, I wanted to integrate it in the default pipeline, so make it as friendly to the actual SOFA implementation as possible for me. Then the cut should be performed on complex shapes, so we are not talking about performing a cut between point 1 and point 2 and just drawing a section plane between those points. I wanted to have more complex shapes. The update rate of the cut should be controllable, so I don't want to remesh every time we performed a partial cut, so I wanted to control the actual update rate. And finally, I was also thinking that it would be nice to optimize the modified mesh and maybe do that in the offline mode rather than doing it on the fly. So a brief overview how the plugin works. Mainly, we have several elements that we want to add to the scene. First of all, it's a cutting tool. That's an object that we add to the cutting tool, to the scalpel in this example on the right. Then for the modifiable object, we add two elements. The first one is a tetrahedral line collision model. You can see it on the right here. So basically, when you have an object defined by a tetrahedral mesh, you can just add a line collision model to register the cut, actually. And then finally, a cutting process manager, the cutting process manager object to perform topological changes. During the simulation, the default collision pipeline detects intersections between the scalpel or the cutting tool and the modifiable object. The coordinates of each intersection, of each unique intersection, is added to the list of all intersections, and then whenever we want to perform the actual changes as you see at the bottom of this picture, we just set the process changes flag to initiate that remesh. The procedure of the registration of a cut is pretty simple, actually. The collision pipeline outputs a collision pair. If this is something new to SOFA, that's something that I modified in the source code. So we have, as you probably know, we have this data called groups, and we do not allow any collisions between objects in the same group. So this thing works in the opposite. We only allow collisions between objects in the same domain. So that was mainly done to avoid collisions or intersection detection between meshes and collision models that are used for registration of the cut and collision models that are used for like regular purposes. So if they're not in the same domain, then we just ignore this pair, this possible intersection, and if they're in the same domain, then we call the proximity intersection algorithm. In my case, it's min proximity intersection because local min distance doesn't seem to work that well due to some things that are quite special to the algorithm. But anyways, once the proximity intersection detects an intersection between two objects, we check if this intersection already exists for this particular modifiable mesh. So if this edge has been cut already, or if we had a previous intersection, then we update the coordinates of that intersection, and if not, then we add the intersection to the list of intersections that we have for this cut. The topology modification step, which is once again initiated with the process changes flag, is mostly performed. Well, this was mostly inspired by the work performed by Steinemann et al. It uses 8 possible combinations for tetrahedral split. Those are that you can see on the left. So it's either a complete or a partial cut, where you split the edges, or it's a combination of split edges and snapped vertices that you can see at the bottom. So if the cut is way too close to one of the vertices, it's much easier to just snap the vertex and create a clone vertex for that particular point to avoid creating too narrow or too squished elements. An example of this tetrahedral modification is on your right. So first we have a model that's at the top. Once we perform the cut, you can see that the tetrahedral structure changed, the mesh changed slightly. That's in the middle, the middle picture. And finally, once the cut is performed, the tetrahedral structure is separated according to the scheme on the left, and the left part falls off the right part, which is fixed in space. Now, maybe a short demo would work. No, it doesn't. So I'll just fall back to this video. Okay. So here we have a scalpel, and of course we have the complete scalpel as a cutting tool. So the visual representation of a scalpel is not quite in line with the part that actually cuts. So basically, the whole scalpel cuts, and right now we cannot distinguish between different directions of a cut. But yeah, this is how the resulting remeshing looks like. Okay. Finally, I'll maybe a couple of words about the framework that I've been working on. It's called Philosophia, and basically it's based on Filament, which is a lightweight PBR engine developed by engineers from Google. It's written in C++, and I thought, hey, this looks nice. Why can I just put it together with SOFA and make a framework for simulation out of it? So I developed a framework that is also open source, and I encourage you to try it out, because basically I've been working on it myself, and I've been working with it only by myself, so it might be a bit buggy. I admit that, but I'm willing to go the extra mile to help you try it out and help you to make it work for your projects. Yeah, so it's written in C++. It provides you direct access to SOFA nodes and objects. It also has a feature for surface subdivision, so we can define an object as you saw in the previous example. We had an object that is defined by the surface to volumetric mesh mapping, and we can represent that surface mesh, which is quite coarse. Was quite coarse in the previous example, and we can perform real-time subdivision using OpenSubdiv. And yeah, shout out to Eric for that. Thanks for the idea. Finally, getting back to the interactive cutting plugin, I'm currently working on integration of that plugin to the to Philosophia. But one of the big challenges for me now is to map textures to the topological changes of volumetric mesh. So for now, it only works partially, and that means that it does delete all triangles and all vertices, but it doesn't create new ones. And probably before I end, a small demo. So you have two examples here, and yeah, it doesn't actually look that, what do you call it? Basically, the framework of GIFs is quite small, so that causes that kind of weird behavior. But you have two examples here. The one on the top is without any subdivision of the surface mesh, and the one at the bottom is with second level of subdivision. Okay. So for the future work, for the SOFA cutting plugin, interactive cutting plugin, it's mostly bug fixes. We have I have some bugs that I want to fix on the way. Mainly that is related to creation of new triangles. And for those who tried the plugin already, maybe you noticed that whenever you perform a cut, there's likely a chance that a new triangle will not be mapped properly. So that's what I've been working on now. Then snapping algorithm optimization, so those snapping vertices can be mapped in a better way, in a more optimized way. And finally, offline remeshing. What I mean by that is we can optimize the mesh that we created, but we don't need to do that actually in real time. Or we can do it in the background and use the mesh that we actually modified while doing this remeshing stuff. And then once the remeshing is done, we can just swap the mesh with the one that was optimized. Yeah. For the philosophy part, as I said, it's mostly topology modification, handling, and texturing of newly created elements. With that, I conclude my presentation, and I would like to thank you for your attention.
Thank you, Vlad. Is there any question from the audience online? For you guys here on site, we're always going to give the priority to the people online. So if you have any question online, do not hesitate to unmute yourself and ask all the questions you'd like to Vlad. Otherwise, either I can. Okay. I'm sorry. Somebody rose the hand here. I'm not sure who did that. So do not hesitate to either write your question in the chat or unmute yourself, because I mean, if you are unmuted, we're gonna see you and definitely leave you the floor. Otherwise, is there in the room a question? I would be happy to ask some, but.
It doesn't have any, so it's free to use. You just check out the repo, download it. I'll probably add GPL license or LGPL. Anything will do. Apache. Yeah, I haven't thought of it, to be frank, yet.
I tried already for fun.
I
tried for the fun to integrate so far into filament, not. And it was awesome. So I'm quite interested. How did you do the build system and everything for filament? But maybe we'll see that later. But that's why I was interested in the license. So maybe I would like to contribute something. So, yeah.
I'm big glad too. Yeah. So it's completely open work. You're free to use it. You're free to do whatever you want to do with it.
Okay, do not hesitate to speak really in the mic. It was barely hard to hear, so do not hesitate. Yeah.
Thank you for your work. I have one question, which is, what is your end application? Do you have one for the cutting? Or?
Yeah, for now,
Can you ask that again?
Yeah, my question was about what was your end application, like if you had one or if it was just exploring different kind of remeshing algorithm.
So mostly my end application is related to surgical simulation, hysteroscopy simulation to be precise. That's the topic of my PhD that I've been working on. So this is more of a side project, so to say. That's why it's advancing quite slowly, to be frank. But yeah, the idea was to implement polypectomy and biopsy for office hysteroscopy. Yeah.
All right, thank you.
Okay, cool. Thanks a lot. I think we're gonna switch just to keep on time. So you'll be in room 1. We'll have to arrange here to see how we're gonna handle the different rooms. Sorry. So we're gonna see how to do that, but definitely. So Vlad will be in room 1 for questions about cutting, and we're gonna continue now with Professor Choi. You should be able to present directly, I think. Professor Choi, can you hear us?
Yes.
Perfect, great. I'll let you share your screen again. Okay, I'm gonna reset and stop there. Okay, yeah, we see perfectly the screen. Let us know, guys, if anyone has an issue here to see the screen. We see that here as well. Yeah, so Professor Choi is actually both of an academic and an industrial partner of SOFA. He's working, as you can see, at Asan Medical Center, University of Ulsan, and as a CTO of LN Robotics. I'm super happy to have you online and soon visiting us also in Strasbourg. So please, the floor is yours. I will start the chrono, and I'll be happy to hear about vascular interventions. Thank you.
Thank you, Dr. Talbot, for kind introduction. Actually, forgive me about this, my view and in environment. I'm on the road, so I am in my car. I'm sorry about that. Actually, today I'd like to share my humble experience with the meaning of simulation technology in the medical, specifically surgical robot systems. So actually, I am a developer of 20 plus years experience in surgical robot development. And recently, about 2 years ago, I opened up a new startup company to commercialize my research results, which is to develop a type of vascular intervention assist robot. I'm going to talk in two parts. So the first one is about my humble view on what's changing in this surgical robot field. So actually, in the beginning, in the past, in the early days of surgery robot, as you can all remember, the focus was on teleoperation, not the automation, which we can easily expect from the robot systems. So mostly it's about teleoperation. And actually, teleoperation is a clear benefit which robot systems can provide. But now, as the rapid advancements in the AI and robotics and computer vision technologies and so on, now we can see a kind of ambitious vision or future. So in this review paper, actually, they say this autonomous robot system is not in the lab, but it's kind of actual reality, and it's really coming future. And I agree with those views. Actually, the purpose is to fill kind of gap between the expert doctors and inexperienced doctors for the patient to have to be benefited from better quality medical service using these automated surgical robot systems. And yes. And if you look at the literatures, I'm sure many of you are aware of these research results. So soft tissue surgery can be done automatically, and it shows better results compared to the conventional, even robotic surgery, which is teleoperation configuration. And also some people already have tried to automate some procedure in this cardiac intervention procedure. And although it's not that good as the result of the soft tissue surgery robot, but still it's very promising result, I think. And I believe in near future we will see very advanced automated procedure even in this intervention field.
50 trials, the robot achieved a 96% success rate.
Let me just skip this one. So actually, there are many groups working on this automation, actually real automation of these surgical robot systems, and I think it's real future and really coming next trend of these surgical robot systems. And next part is my humble own experience, which is about vascular intervention robot. And our topic is coronary intervention, so called coronary angiography or percutaneous coronary intervention. So in this procedure, conventional procedure have limitations as shown here. So to alleviate these kind of limitations, many people think about using robotic technology in this procedure. So it's called robot-assisted coronary intervention, robotic PCI. And so if we look into the procedure, into the subtasks of the procedures, then we can easily see that there are many subtasks for which doctors need to think and do with their own brain and with their own hand. And for the hand, we can provide robot. So for the brain, now we are talking about AI. So we can utilize the computer systems in the robot system to provide better intelligent functions for doctors to assist their brain functions in these decisions and motions in this procedure for better outcome of the procedure. So actually, we started our development since 2014, and then in 2019 we could have our first clinical trial of our first system, and it was in our hospital, and it was pilot clinical trial, and it was only in 2 cases, but the 2 cases were successfully performed without any accident or adverse events, and we could confirm that this kind of system we could develop with enough safety and feasibility. And now after that we are into the version 2 development. So in this version 2 we thought we devised a few upgraded functions with which we can, in a sense, compete with our competitors, and in a sense we can provide better and really meaningful clinical effectiveness, clinical outcome for both doctors and patients. So I'm not going into the detail of these technologies. So the first part was haptic interface for better manipulation and better dexterity of the doctors in the procedure. And the second part was about this advanced mechanism with which we can apply these systems for larger, wider areas of the intervention procedures. So it seems just one big picture, but actually if we go into the picture, then we can find many detailed different procedures with different level of difficulty, and current robot systems may not be enough for that, for covering those wider areas. So we are targeting to have our own system to cover wider area of these procedures, so-called complex procedures. And also we tried to develop some technology in AI, both for the control and the monitoring, automated monitoring. So for the control, we tried implementation of this reinforcement learning-based autonomous navigation of the instrument, which was quite straightforwardly could be implemented. And then we also developed new techniques for image monitoring for doctors, better situation awareness. But actually in the real market or a current stage, AI is not yet fully kind of adopted. So we can develop and we can do some work with AI, but for the actual clinical practice, still the kind of level of technology used in clinical practice is kind of semi-automated. So actually, during this whole development, all the times, always my kind of agony was this direction, these functions, will those really benefit doctors and patients? Because as engineer, we can enjoy the development, but still it's medical device and it should provide clinical effectiveness. So it was always question to me, and fortunately, change in the clinical society is that now it seems that they are opening the field for adopting this robotic technology. And as I told you before, the level of automation in clinical practice is just kind of semi-automatic procedure, not intelligent, autonomous, full autonomous procedure. But still, with this semi-automation, doctors can find that it could reduce the use of contrast agent and fluoroscopy time and radiation dose in patients, not only doctors, but in patients. So it becomes a real benefit for the patient using this robotic technology. And some doctors say that now we need to resort this robotic technology to have better meet the patient's needs in this cath lab. And also they are looking back on this simulation, the meaning of simulation. So I'd like to, time is clicking, but I'd like to summarize what and why we need to look back on this simulation in this field. So as you are well aware of, Da Vinci robot system has long developed, well-developed simulation for their training. And in the past, the training simulation, when we say team simulation, then it was mostly about the training. But actually, even this slide was made in 3-4 years ago. So now I believe they must have very much upgraded technology. But now it's about patient-specific. So patient-specific simulation. It's kind of rehearsal of the actual procedure for each patient. So now we can do that. With the upgraded simulation and image processing technologies. And also now
디지털 트윈은 다양한 상황을 시뮬레이션함으로써 시간 비용 이러한 메디컬 트윈은 생체 실험이나 시험 그럼에도 불구하고 현재 심혈관 분야의 메디컬 트윈은 다음과 같은 기술적 한계가 있습니다.
Okay, what I was going to tell you about with these slides was the meaning of medical twin. So it's kind of I frankly think it's kind of decoration term, but it can be really meaningful if we could implement really elaborated high-fidelity simulation, which can actually not exactly but very precisely synchronize to the actual patient status in real time. So actually, we are talking about not only the training and rehearsal, but also using this technology for the monitoring of the actual procedure in line with this simulation. So I think the simulation technology is kind of real future in this medical robot field, which can open up new possibility. So we use robot, we use AI. So we have computer, and then we can do simulation, and then that simulation can be meaningful in many sense in this surgical robot field. That's what I'd like to share with you. Thank you for your attention.
Thank you, Professor Choi. Is there any question in the online audience? I would be happy to take one, and do not hesitate to unmute yourself, as I said before. I see some reaction here from Wang Yu. First, just while maybe if there is some people like preparing that question online, just to say that LN Robotics associated to Assad Medical Center is like really one of the, for the last 6 months, especially one of the main contributors in SOFA, not only in SOFA, but also in plugins. So that's something which is really nice to see the collaborations between open source projects, medical robotics, and even like academic and industrial. So that's something that we are super happy and proud of. And maybe something to add also, Professor Choi, you maybe did not say that, but globally it's a topic where there is a lot of recruitment. So if you are interested as well to like join LN Robotics or adventures in South Korea, it's something which is definitely possible. So do not hesitate to get in touch. Is there any question in the audience? Maybe...
I have a question.
Yeah, go ahead, Chris.
Yeah, no, just how do you, so thank you very much for this presentation. Maybe there is one challenge is how to make the simulation, how to I would say correct the simulation so that it follows the image. And did you have experience on that? For me, it's a big challenge. How to make the simulation of the catheter be exactly as it is in the like how you see it in the image.
Actually, that's kind of homework which I asked yes, but for that subject, I can explain this. So actually, in conventional medical practice, doctors were using a kind of image registration technology to have preoperatively obtained patient history with the image overlaid on this fluorescent image, but it was not dynamic image. It was just overlaid image, and doctors actually do not use that technology very much. So what I and my colleagues at India and friends work on is to have that be upgraded to the kind of 3D dynamic roadmap. So for which we can think of two methods, two ways. So first one is to have that registration for the deformable registration. But actually, many people already tried to make that deformable model registration, but it works. It works. How I should say, it works good, but not enough. So now, what we are thinking is, if we could implement the simulation with very high fidelity. Actually, for that, many researchers at India now are working on that. So then with the robot system, so if in the manual conventional procedure, we don't have any measure to connect the real world and the simulation. But in robotic procedure, we have robot system. So the robot system can sense the motion of the instrument which is going into the patient body, and then feedback that signal and information to the simulation. So at least in terms of input data, we can have synchronized data. Now the topic, the homework, the issue is how we can simulate afterward. So I'm not sure how far we can go, but if you look at the initial results of the simulation of the casters and wires, and I think in a few years we could really feasible result. So and then I believe we can actually implement a good example of surgical twin or medical digital twin with this simulation technology.
Thank you very much.
Thank you very much. For more questions, so we're going to keep the breakout rooms open after the four presentations. You will find so Professor Choi in room number 2. We're going to have now the presentation of, it's actually going to be like joint presentation from Insimo about node identifications and suturing in robotics. So both François and Il will make the presentation. Thank you for, so they are on stage with me. I'll let you up this mic so that it will be easier for you to speak. The floor is yours, and do not hesitate to prepare questions again from especially the online crowd. Do not hesitate to unmute yourself at the end of the presentation and ask all the questions you'd like.
All right, hello everyone. I'm François, and together with Lille, we are going to present you some of our recent research work or developments on suture simulation for robotic surgery. And this presentation will be in two parts. So the first one will mostly focus on an article we have published together with Christian Durier and Barbara Seliger from both INRIA Defrost team and IHU Strasbourg. And the second part will be carried by Lille, and we'll focus more on the node identification part. So before we dig into that, just a quick overview of what we are doing. So we both are working at Insimo, and it's a company who's doing simulators mostly for surgery training in different medical fields. For the main topic will be like eye surgery simulation, but we also develop like simulators for lumbar puncture, robotic surgery, and also like for echographic sound imaging analysis. And just a quick overview about what we're doing like in terms of research work and open source collaboration. So we maintain our own private work of SOFA, and parts of it are actually publicly available. We presented that 2 years ago at the SOFA week. So yeah, you can reach us out if you have any question about that. Anyways, so back to the main topic. This is the article. So we published this year that I'm going to give you an overview about. So essentially, this article tries to the motivation for this article is to try to address several of these points, which are the fact that in robotic surgery, there is no force feedback for the apprentice or for the surgeon. So because of that, there is an excessive amount of force which is applied by novice surgeons when they basically get their hands on the system. And we notice that actually we can sort of find a surrogate to force feedback with visual input, visual force feedback, which actually has been demonstrated as a way to reduce the force applied by practitioners when they see like this sort of visual input. And we also wanted like to provide a simulation exercise for suturing that actually can be used like to train outside like the operating room. So our contribution is like at 10,000 feet view, but I will show you a video afterwards. But basically, what we provided and we needed to provide is an as realistic as possible suture thread simulation model. And in order to do that, we combine like beam theory with which is like Timoshenko beams, and extended with a co-rotational filter to accommodate for large displacements. And in order to, let's say, like to cancel like, the stretching displacements of this model, we also needed like to implement like a hard inextensibility constraint to actually be able to model faithfully like a suture thread. On top of that, like to do like the interactions, we implemented like what we call like a smooth collision representation, which is based on a cubic basic curves geometrical model. And from that, actually like mechanical accurate model, we could actually directly map the constraint forces applied on that suture thread model to visual cues. And we demonstrated that like by comparing like our on suturing task or simulation with what is happening like on a real Da Vinci system. So this is the video I'm going to show you now, and it's actually an extract of a video that we provided like for the article. So you can see like on the left hand side of the video like the gesture performed on the, maybe I can go full screen, that would be better if that works. No, it's not going to work. And on the right hand side, like the same suturing task performed on the simulator. So you can see like our system like supports like the fact that to do like multiple superimposed knots, and actually there's going to be like 3 knots performed, I think, in this video. All right, here's the third one. All right, and we also implemented like some other features, like to the fact that you can break the suture thread, and also like more complex like suturing exercises, and you can actually see like the color code like which is applied like both on the tissue, the tools, and suture thread, which actually directly map like the constraints that are applied on either the thread, the tool, or the tissue. And I think like, yeah, it's also like needle bending is also like a common error that is performed by novice apprentice when they apply too much force on the needle. So yeah, I think that's it for the video. And now Lil is going to talk to you about, okay, next slide. Yeah, he's going to talk to you about like knot identification for robotic surgery.
Okay, thank you, François. So in this second part, I will talk about knot identification in the context of robotic surgery. So, of course, nowadays we are able to perform knots with robotic in robotic surgery, and we understand that a poor suturing technique can lead to many disastrous consequences in an operation. And so, to provide the best simulator as possible, we understand the need to obtain in real time the type of knot made by the user, and we also wonder, did the user make any mistakes? So it may seem not complicated, but it is, because the first choice the user has to make is, will I do a simple knot, a double knot, or triple knot just by varying the number of loops around the tool, as you see on the video? And talking about the loop, he has the choice also to make the loop in clockwise direction or anti-clockwise direction, which is a very important factor because this determines the nature of the knot. So I will talk you briefly about the knot theory. So it is a very mathematical topic, and it has little to do with the suture simulation in general. But as you know, a knot is a piece of thread which has a spatial conformation in space. And in order to study a knot, the first thing you have to know is that you have to project it on a 2D plane, as you see on the figure. And this comes from the fact that a few years ago, we didn't have all the visualization tools we have today, the 3D visualization. And so we obtained what we call a knot diagram, as you see on the figure. And with this knot diagram, we can identify a knot. So this is how it works in the theory, and it is exactly the same in our simulator. So at the moment of the simulation, we retrieve the spatial conformation of the thread in order to project it in 2D and study it later. So once we have this projection, we can look at different factors. For example, the number of crossing on this projection. Here you have 3 crossing on what we call the trefoil knot. We can look also at the direction of those crossing on many other factors. And with all those factors, you can have a sort of identity card of your knot. This identity is defined by a unique polynomial, which is called the Jones polynomial. So you have an example of the Jones polynomial for some famous knots. And the Jones polynomial is also a very powerful tool because it allows us to distinguish between a simple knot with a clockwise loop, for example, and a simple knot with anti-clockwise loop. So we have an algorithm to detect the knot in the simulation, but it's not the only problematic because yes, you may know that a suture is composed of a superimposition of several knots. The best way to do so is, for example, to begin with a triple knot, clockwise or anti-clockwise, and then to tie 2 simple knots above it in 2 different directions to solidify the suture. And the main problematic here was to identify each knot of the sequence separately and to keep it in memory in order to summarize what the user has done during his training. And so the knot detection algorithm allows us to detect some standard mistakes in robotic surgery. The most common one is the rabbit ear mistakes. So it occurs, as you see on the video, when the user leaves the strand lying around and gets it stuck inside the loop when tightening. And so, as you may see, the rabbit ear name comes from the shape of the thread when it gets stuck. And our algorithm can predict such events. So our algorithm is not specific to robotic surgery because I had the chance to implement it in a cataract surgery simulator also, and it can open the door to many perspectives, I think, in other fields also. So we hope you enjoyed the presentation. Thank you, everyone, and do not hesitate if you have any questions.
A lot. We were a bit late, so we still have time for one question. Is there a question online? I have already like 5 on my own note, but is there either online? I'll check that, or in the room. If there is, do not hesitate to take the mic and ask for it. What do you see? Okay. Someone, please, when you are raising the hand, just so you may directly unmute yourself. Stefan? Okay. Stefan, can you unmute yourself maybe?
Hey guys, no, actually that's a question for the previous talk. And
I'm sorry, Stefan.
I remained raised, but
all right. I'm
perfect.
sorry, I don't see that in the. I mean, it's hard for me to see the hand reason here in the interface. Yeah. Yeah. Go ahead.
Hi. So thanks for the presentation. One, I guess it's more of an open question, but have you had a chance to compare visual haptic feedback against like conventional haptic feedback, kinesthetic feedback?
No, it hasn't been carried like in a proper like studied fashion, like the way to compare these two inputs. Mostly because it would require like to to carry a proper study, and I think it's kind of difficult like to get this standardized way of collecting data on that. And I guess it would also require to implement force feedback also on our model. So I'd say it's it's an open question.
In your opinion, would it actually visual haptic feedback compared to kinesthetic feedback? Is it possible to be a valid substitute?
What do you mean, like if it's better or in terms of compared to?
Yeah. How's it?
I don't think it's better. I think it's different, definitely. And but it's definitely true that having some visual inputs actually naturally like gives you like a kind of artificial sense of touch. So and the fact that it reduces like the amount of forces applied, it's actually something we experimented also like on ourselves when we developed like this sort of simulator. So I think it would be helpful to have that like Barbara.
Thanks a lot.
Maybe you can answer.
Barbara Seliger. So first of all, congratulations for all you developed. And I'm a bit biased because I'm the surgeon involved in this project. And so we decided regarding your question that we would not equip a robotic machine with real-time measurement during the gestures we did, because there's already studies around that say novices exert around 40% of excessive force, and with a pure visual feedback you can reduce that to about 20%. So in that simulation concept, we have the advantage of no real mechanical system, and it allows to, in real time, measure the forces regarding the constraints on the elements for not elongating. So that allows to measure the forces and transform them, and we don't need this in a simulation environment in order to reduce the training needed for robotic surgery.
Passed around, I guess. I was just mostly interested in whether like this kind of learning is transferable. So if a training learns to perceive the scene with by the means of visual haptic feedback, will it lead to smaller forces when he actually gets to the real scene?
François could answer that as well, because we trialed with several surgeons. It's not published, and we didn't do a systematic evaluation yet, because still working on some metrics. But what we saw with the surgeons trialing the system is that they quickly realized how much force you can put before a suture breaks, and that can translate to a real scenario, and everyone would say that would avoid hours of not tying and breaking things.
Thank you. There will be, if there is other questions, I saw that Paul and Davide were actually unmuted. So if you have further questions, do not hesitate to join us in the room number 3 after the last presentation. That will be Arnaud presenting here. That's going to be the update and the next steps from the developments going around Sonics, which is the coupling of SOFA and Phoenix. And yeah, that's, as you can see, a joint work, especially and here led by University of Luxembourg. Welcome, Arnaud. Let us know if everything is fine. I think we can see your slide. We can even hear you, so that's perfectly fine. I'll leave you the floor. I start the timer, and I'll let you start.
Hi. So you can hear me?
Yep.
Okay. Thanks. So I have no visual on the time, so I hope to make it quick.
Yeah,
So as Hugo said, it's a joint work between the University of Luxembourg and INRIA at Strasbourg. So it was mainly led by me and Sadati on the other side. And so the purpose of this work is really to combine the strength of SOFA and Phoenix to create allows to make complicated material modeling in SOFA without to code any stuff. So that would be quite amazing for not great coder, let's say. So the motivation, so in SOFA, usually how it's done, the finite elements, so you can go in the C++ code, you can find some element.h where you have the geometries. So the geometries are usually quite simple. It's tetrahedrons, triangles, hexahedron. But there might be some lag. For example, I didn't see any prism or some complicated geometry that we might need. Also, the shape functions are quite poor. Usually, you just have linear shape functions. So we could tackle higher order shape functions. And similarly, for the quadrature interpolation, it's usually the same scheme at order 1. Another problem is that we usually have few material models. When you go to hyperelasticity simulations, for example, you might need some more complex model for this. And similarly, when you have to write down your C++ code, you usually need to derivate strain energy density function. So this one is for Cervin-Kirchhoff, so it might be quite straightforward to do this one. But when it gets to more trickiest ones, such as Bose-Apfel-Ogden anisotropic, it can get really messy and sometimes really difficult to do if you're not that great at math, like me. So what we propose is to use the Phoenix project. So Phoenix project is not similar to SOFA because the aim is quite different. It's really based on the finite element research. But the good thing they did is you can completely bypass the C++ and write everything in Python. So basically what you will need first is to define your topology. So as you can see, it's one line of Python when you define your family of finite elements. So here it's Lagrangian. What you will work on, so tetrahedron, and for example, linear tetrahedron, so order 1. Then what you write down is your strain energy density function. So here it's the previous one I wrote, so Cervin-Kirchhoff. And then after you can write, you can sum the forces, the inner forces, also the body forces and the traction that can apply on the material. Basically, if you want to change the elements, it's super straightforward. You can just change here instead of Lagrangian, take serendipity, for example. You can work on hexahedron of order 2, so quadratic, and you can change the strain density energy function for Neo-Hookean, for example, and change the quadrature interpolation. The only thing you need to write after is that you will take the derivative of this function with respect to the displacement. Then you will take the Jacobian of the previous derivative that are usually a need to compute the next tensors. After that, you just run this command, ffcx material.py, which contains all the information about the material. It will generate some C code, which is quite optimized and will be used to assemble the residual and K tensors, but the local ones. So what is done usually in SOFA? So when I'm speaking about SOFA, I'm speaking about the Caribou plugin. I will come to this later. So when you go in the C code, there usually this add force function and the add K to matrix function, but the pipeline is the same. So you loop through every elements. Through every elements, you look for the Gauss nodes, and on the Gauss nodes, you compute your tensors that are in need to compute your global stiffness matrix. So what we do now by this coupling, you just go through every elements and you assemble the local tensors that is outputted by the C code. So it's really quite well because we don't need any expression of the derivative of the tensors and no need of taking care of the shape functions too. And so finally, we created this hyperelastic force field. Hyperelastic force field. We tuned it to fit the Phoenix pipeline. And in the Python code, you can just add this object using your Phoenix material. You precise the template, so the elements. and then you can precise the material properties that you will use. And so that's, I can hear some sound, so maybe someone can mute himself or herself. And so that's one result we had. So it's a haptic simulation where we control a surgical tool and we come to collide the lever. So this lever is modeled using this Ozapfel-Ogden anisotropic material. So as far as I know, I never seen some implementation of this in SOFA. Okay. So the result of this research is, so we are currently publishing those results. For the moment, it's just a preprint that you can find on arXiv. It's currently under review. Our branch is called Phoenix Features, and it's hosted on the Caribou plugin that was a previous development at INRIA, which kind of facilitate the finite element implementation. It's much more straightforward than in the current SOFA code. I will quickly sum up the points of the research, but basically we have machine down precision equivalency with SOFA and Caribou for linear and quadratic tetrahedron, and also for linear and quadratic hexahedron. We tried it with a Saint-Venant-Kirchhoff and Neo-Hookean material model that were already implemented. So we did it for a cantilever beam and the manufacture function. I don't have the time to dig in, but if you know it, it's quite a great validation. And we also validate our implementation with FEBio, with also Saint-Venant-Kirchhoff, Neo-Hookean, and the Monet-Rivlin material. And as I've shown previously, we just also have a visual, I mean, we don't have any validation for this complex simulation, but we show that it was possible to be done in SOFA. For further developments, we plan to merge our branch in the master branch of Caribou and to provide more documentation. A few problems that we still have is we still need to do some copy paste in the C++ because you generate your C kernel, then you do a pointer in the force field toward this, but if you generate a new kernel, this pointer might not be valid anymore. And if you also add some new material model, you basically need to copy paste those pointers direction in the code. So that's quite inconvenient. We already have some tracks on how to solve this matter, but it might take a bit of time to solve this. We also plan to have some CI/CD tests to be compatible with the current SOFA master branch and Phoenix branch. And for further work, we plan to really tackle more complex elements such as shells or prism. And we would be really happy to have first test by first users and to collect some feedbacks. Hope I was not too long. Thank you very much. If you want to write me or Sadati, you have our contacts between. We also are active on the GitHub discussions if you want to join us. And you can check the paper for more details. Thank you very much.
Thank you, Arnaud. So yeah, definitely do not hesitate, guys, especially Arnaud here, since you're the last speaker, to drop also your contact email. But for anyone who wants to really get close to Arnaud, there will be the room number 4 for Arnaud later on, and benefit from that because you'll all soon like leave for a far away foreign country. So do not hesitate to grab him. There is already one question online from Christian who is asking, can your models include incompressibility? I guess it's penalty incompressibility that could be included.
Yeah, so penalty can be carried on, I think, quite straightforwardly. We would also like to work on the mixed formulations, such as a UP, for example, but we might need to get some tricks on how to solve the problem. I mean, you need to separate the displacement and the pressure field, and for the moment, we cannot do it quite straightforwardly in the Caribou, but it's a track, and I'm sure we should be able to solve this problem.
Okay, thank you. Thanks a lot. I had several points. So first, about the euro, that there were actually some copy paste required. Can you just evaluate the amount of copy paste? Like, is that one code, like one function to copy paste, or is that the two, like at force and d force, or is that like more than that that is actually needed here for having the C++ code working so far?
So thanks to Sadati, it's quite few copy paste. Honestly, you don't need to copy paste the whole add force and add k. it's just, I think, yeah, it's like eight copy paste of 2 lines every time. So it's just really to copy paste the pointer and just to create your material. I mean, it's just really few copy paste, but still it's hard to sell when you want to say to people just use Python. You still need to do some copy paste in the C++ code. Yeah, we would like to improve this. They actually did it in Phoenix. They use Numba, which also could be a good lead to continue this.
Okay, cool. And yeah, and you already mentioned that, but yeah, definitely having that coupled with Caribou, we already got several times the feedback about Caribou that it's easing the reading of continuum mechanics in for especially for mechanical engineers, or I would say mechanical profiles. So I think it would be great to have it, as you said, merge into the Caribou master. That would be and with documentation, it would be really awesome. Is there any question in the crowd, in the audience online, even on site if there is? Otherwise, we are going to create the 4 breakout rooms. I'm going to actually create them right now, and you should the 4 speakers should actually be like dropped into the associated room. So I'm going to share just as a reminder I'm going to take the lead. Sorry, Arnaud. I'm sharing the slide again. So that was for the program of this first session. And so room number 1, you'll find Vladimir. Room number 2, you'll find Professor Choi. Room number 3, there will be François and Neil. And room number 4, there will be Arnaud. We'll just need to arrange here locally, since we are 2 in the same room. We might just one go in corner and so on. But are you already? If maybe François, if you can stay there, and we'll use the room here to make the discussion, if it's fine, or use your computer. But yeah, the 4 rooms are being created. You should be people are already getting in the rooms. Do not hesitate to join them and ask the question to the speakers. Again, as it is displayed, Vladimir 1, Professor Choi, room number 2, 3, François, and 4, Arnaud. Sorry? Yeah. So yeah, I'm gonna please move. Everybody can now move in breakout sessions. We're gonna move as well. So and see you in about 20 minutes after the coffee break. It's exactly 18 minutes. Yeah. See you.
Okay, so my question is, I'm a beginner with SOFA, and I was wondering about the differences in the physics between real life physics and the physics in SOFA explicitly. So the real differences if you want to apply a system trained on SOFA and then use it in real life. Maybe
So,
where can I find?
I think the best for you would be to join the session with Arnaud to ask directly the question to Arnaud. You could even do that in French. I think there is a French crowd in the sub room number 4. Do you want me to drop you directly in the room?
Oh yes, that would be nice. Thank you.
Okay, cool.
Merci.
Great. Quentin, can you hear us? So far, I can't hear you. I do a request for unmuting.
Okay, can
yeah.
you hear me now?
Yeah. It's not very loud, but yeah, we can hear you. Sorry?
Can you hear me now?
Yeah, it's better. Yeah, thanks. Welcome back, everyone. So what I'm gonna do here is that if some of you guys got not enough time actually to discuss with others in the breakout session, I can I will restart some of them. So if you want to go there and chat privately with some guys, this will allow anyone to actually take some time of discussion. So I'm restarting them. The main stage will continue now. You should have been noticed that breakout rooms are available, but so we are going to start the second session of the day, which is the first out of the two, focusing on soft robotics. And it's actually my pleasure to welcome Quentin from ETH Zurich, and it's going to be close to a topic that has been presented a bit earlier by Professor Choi. We're going to talk again about medical application, even possibly medical robotics with magnetic continuum robots. So I'll let you the floor, Quentin, and there will be obviously time for question right afterwards.
All right, thank you, Hugo. Thank you very much, everybody. So I'm presenting on behalf of Roland today. And yeah, as Hugo mentioned, what I'm going to talk about is magnetic continuum robots. So what we're doing at the multi-scale robotics lab ETH Zurich is we are doing remote magnetic navigation for minimally invasive soft tools such as catheters or guide wires. And the machine you see here on the video is the Navion, and this is our last electromagnetic navigation systems that our lab has developed in collaboration with Nanoflex Robotics, which is a spin-off of our lab. And what the machine is essentially doing is controlling magnetic fields, and you can see the field lines here, by generating currents through electromagnets. So this machine has 3 electromagnets, and the field is used to steer the tip of a magnetic tool, which is essentially a flexible tube with a magnet at its tip. And what we're considering here with this machine specifically is for neurovascular intervention. So we insert a magnetic guide wire from the femoral artery, and we control its insertion through an advancer unit. This is the device you have seen before. And we use this advancer unit in the magnetic field to guide the catheter, to guide a catheter such as an aspiration catheter that can be used to remove a blood clot, for example. So the goal here is to reach deep region in brain with the guide wire. So and this is what you see here being done on the video. And once the guide wire reached the region that you want in the brain, you catch up with the catheter, and this is how you, for example, remove a blood clot. So here the task here is to reach this clot right there, and obviously using the magnetic field and then pushing the guide wire to reach the clot and then reach the clot with the catheter. And the whole machine is operated by a neurosurgeon who uses the fluoroscope image as a feedback, and of course that can be, the whole operation can be monitored from a control room. All right, so that gives you an overview of what we're doing with these machines. And as a matter of fact, we use the Navion already in vivo, and this is person you see here in the picture is Dr. Philipp Gruber. Is one of our neuro radiologists from Kantonsspital Aarau, and he's manipulating the machine here to guide this magnetic tool in the neck region of a porcine model. Now the question you may ask yourself is, why do we need SOFA? Why do we simulate anything in the first place? well, we actually started considering SOFA to simulate these tools a couple of years ago. And our main motivations are, well, we want to be able to simulate and validate new concepts for magnetic tools. And I hope this is pretty obvious, right? I mean, it's always much easier to simulate something than to actually use a real machine to steer it, especially in our case where the machine is usually expensive and difficult to design. Also, it's a very good tool for training. So we implemented here. I mean, this is an example of an early game we developed to get used to the mechanics and the kinematics of these tools. And for those of you who attended 2 years ago, we also trying to use SOFA to simulate other kind of magnetic devices, not necessarily medical. But essentially for us, the advantage of SOFA is that it's open source, it's real-time implementation, which is very important for us, and it can actually interface relatively easily to our software infrastructure. And so to give you a brief overview of how our simulation framework is working, I'm trying to keep that as high level as possible. But essentially, we are simulating the dynamics of our tool and its interaction with the anatomical environment with SOFA and the beam adapter plugin. And the input that is needed for this simulation is obviously the magnetic interaction with the tool. And the input we use here is TI, which is the torque applied on the magnet. And the output of this model is the tip position. This is what is interesting for us. And so to obtain the torque that is actually on the magnet, we can. It's basic physics. You just look at the cross product between the magnetic dipole of the magnet Mi and the field generated at the position of the magnet B of Pi. To obtain this magnetic field, we use a very simple calibrated linear model of the magnetic navigation system, which relates the current in the electromagnet I to the magnetic field generated at any position P via what we call an actuation matrix A. And these things are implemented via a pattern controller in SOFA, and we use internal libraries that we developed in-house for the model. So since we first used SOFA, so as I said a couple of years ago, what we really focused our effort on, especially recently during the last month, is focusing on two things. The first one is to have a quantitative experimental validation of our new navigation system. And you see the experimental setup here on the left. What we want to do is essentially navigate a catheter in a flat model. So this is what you see here. We have an overhead view of this model, and we control the field and insertion retraction of a catheter in there. And we want to be able to compare our simulation to the real experiment. And to do that, so we use SOFA, we use ROS for visualization. This is the image you see on the right. And as a matter of fact, the simulator I'm going to show you here is available online. So this is an overview of how this validation looks like. So on the right-hand side is the real video, and on the left-hand side is the simulation. And well, we already knew qualitatively that worked pretty well, but what we did recently is really to extract the tip of this catheter, measure its orientation, and really try to have more quantitative results on how well it works. And in flat model, it works actually extremely well. So this is good for us because this is typically the kind of model we use to iterate on the design of our catheters and guide wires. Now, the other thing we're looking into is using this simulation to design and optimize, to optimize and validate designs for new tools. And what you see on this video is essentially replaying the same user input, but for different design of the guide wires. So you have a relatively short flexible tip, a medium length flexible tip, and a long one. And we see that the behavior is completely different when it comes to take the turns in this model of an aneurysm. And the other thing that is really interesting for us is that we're really trying to integrate SOFA into our more globally in how we use these tools, how we evaluate them. And what we did after we tested our device in vivo is to extract the anatomy of the neck region of the porcine model we navigated into, try to reproduce these results in vitro, and try to reproduce again these results in simulation. And being able to have these 3 videos side by side was something really we were looking into for a long time, and we're quite happy that we managed to do that. And now the idea would be that we could also go the other way around, and now from the simulation try different designs and try that in vitro, and eventually making the use of animal models more efficient, because these experiments are costly and sacrificed animals. Now, the other thing we're looking into more recently, and something that we haven't completely solved yet, but is we're really interested to be able to estimate interaction forces between our tools and the anatomical environment. It's particularly important for us because we want to be able to assess possible damage to the tissues, and of course this is an essential point for designing new magnetic tools. And here the forces, the video you see here is just by somehow using the information that is included into the Lagrange multipliers that are computed when integrating mechanical constraints imposed by the collision environment. And in that case, you can see in blue the radial forces, and in red the tangential forces. And last but not least, we also are looking to now, again, actually, because this is something we looked at a few years ago already, which is the use of magnetic needles for deep brain stimulation. So in that case, the magnetic tool is used to penetrate into the brain tissues, and we use the magnetic field to take curved trajectories to reach deep region in the brains that we want to simulate electrically, while avoiding some obstacles, anatomical obstacles. And we would really like to try to use SOFA here again, both for the design of the tool to assess deformation of the brain while inserting the tool, and eventually interaction forces as well. Now, what I've presented today is published in the Robotics and Automation Letters paper that was first authored by Roland. And we had the chance to actually present this work also at IROS 2022 in Kyoto last month. Again, as I said, all of the simulation results I showed you today, you can access that online. And that's it from my side. Thank you very much.
Thanks a lot, Quentin. I saw some impressive faces in front of me, or impressed faces, sorry, in front of me in the room. Is there any question in the audience, online audience, or on site? Do not hesitate to unmute yourself if you have some and ask some questions. First, I must say that I love the idea of having like optimized design based on simulation for placing. I guess do you have already like some result or some conclusion about where to place those EM sensitive pieces on the catheter that would be ideal, or is that really case dependent on where and what shape is the algorithm, for instance?
Yeah, that's case dependent. I think you have a lot of room to explore there. I mean, we also started looking into magnetic concentric tubes. That's something we did with Quentin Perron as well. And I think a simulation framework like SOFA would be ideal for that. I must say we didn't dig that much into that yet, but I mean it's an immense field of possibilities for sure.
Yeah. And is there anyone? I thought. I mean, we have people in the room like Paul, who seems. I mean, it's not only catheter, but it's also needles. I think it could be interesting to chat about that in a private room. But yeah, just so that you know, and that's also for everyone in the audience. But about BIM models, there is actually quite a lot ongoing for updating, improving performances of the models that you are using, the Timoshenko BIM model. And there will be also discussion time this week, later on this week. Later on this week, to actually plan to update, possibly the collision model and to improve the way we detect it, we respond to it in a more efficient and also realistic way. So what you showed at the end with the Lagrange multipliers, tangent, so normal and tangential, there could be also a topic of further collaboration about that. That's cool. Anyone? Any question about? I have like 5, 6 of them, but we won't. I mean, I will join you in the room afterwards, Quentin, definitely. Is there anyone? No, not here. Online? Maybe could be after. I guess there will be also companies and I mean partners that will join you in the room. Thanks a lot for Quentin for the presentation. To keep track of time, we're going to move on to the next presentation. Mikel, you can already present. I mean, you can already share your screen if you can. We can see you, perfect, and you can share your presentation as well. And as soon as you're ready, I will start the timer. So it's gonna be a presentation from KCL. We move now from Switzerland to UK, and it's gonna be still obviously soft robotics and tendon-driven eversion robot. So we could see your screen for a moment, but I mean I lost it. Okay, sorry.
Yeah.
Perfect. It's coming, loading, and. Yeah, if you go full, perfect. We can see the slide. Okay, the floor is yours, Mikel. Thank you for the presentation. Go ahead.
Okay, so hello everyone. My name is Mikel, and I don't know why it's like. Wait. Yeah, no, I think.
Okay, cool. I was gonna say you're muted. Make sure you get your mic back. Perfect. It's loading. We should see your slide in a few seconds. Yeah, that's good. Go ahead.
So hello everyone. My name is Mikel, and we've been working on trying to create a high-fidelity model for one of our designs we had in the lab here for early breast cancer detection, called the MammoBot. So a bit of introduction here to this type of robot. So inside of robotic, there are like a lot of ways of understanding the robots and modeling this type of robot or like designing them. One of the new designs that came out based on growing robots is the grow by eversion. So this means that instead of pushing the robot from behind and adding material at the bottom of the robot, we are adding this material to the tip of the robot, so we are avoiding this kind of translational motion, like this friction caused by the translational motion at the base of the robot when interacting with the environment. But one of the problems with this is like sometimes they are not reliable, so they will try to go anywhere they can find a hole. So one of the ways they use, they insert some kind of steerable device inside, in this case, for example, a catheter in our case. And using this active steering, we can change the structural stiffness of the material in order to move the system in the directions we want. So a bit of like an examples here. So we have our real setup here in the left, and how we try to implement this based on SOFA, and how we have in our case two systems, as I was discussing before. We have the cell growing sheath. So the growing sheath at the end is a thin wall structure. In this case, we decided to make it cone shaped so we can we could distribute the pressure easier and make the system grow more stable. After some experiments, we decided that this was the best way of modeling this. And the tendon and the tendon-driven steerable catheter at the end is a soft catheter, and the tendon is imagine as an edge that crosses the whole catheter from the tip to the bottom of the robot. And basically, in the real system, pulling or pushing this catheter, we will steer the pulling or pushing this tendon, we will steer the catheter. And in SOFA, to simulate this, we change the actual resting state of the tendon to steer the catheter in different directions. So a bit of an overview in general of how the implementation was done. So we wanted to analyze if in SOFA we could simulate these interactions that were given in this very small scale between the catheter and the sheath using the SOFA's collision pipeline here. So at the end, we have two collision nodes, one from the sheath and one from the catheter, interacting between each other using the default collision pipeline from SOFA. And we have the two physical nodes simulating the actual physical behavior of these systems on the real setup with its own stiffness and damping values that I'm going to discuss a bit later how they were. And then we had the SOFA Python 3 library here, or plugin, controlling the different parameters we want to control using, in this case, keyboard commands, because we thought this was like the most basic and simple implementation. So anyone could take this library and be able to play around with our steerable and self-growing system here. So with these keyboard commands, we can update the velocity of the mechanical object, update the pressure field on the sheath, update the tendon steering, so pull or push the tendon, rotate the base from both systems, and we can add loads on the tip to see how the physical properties of the catheter work under a lot of pressure, for example. And at the same time, for our experimental designs, we decided to use Python 2 to record the tip position on every animation step, so we can keep track of things like the curvature and the bending angle, that are the things that we are going to analyze to validate this system against our proof of concept real system. So we did some experiments here. So we did 3 main experiments in this case. So we have the tendon modeling first. So we first decided to test each of the systems independently. So in the first case, this experiment was taking the catheter and pulling the tendon into different levels and recording the values of the curvature for each of the pulling positions of the tendon, and trying to model the physical properties from the catheter and from the tendon, deciding which was the proper stiffness for this system alone that was the most closely to the real system. After this, we decided to perform some experiments on the sheath only. So for this we decided that one of the things we could do here was to grow the sheath until its maximum position, and then turn on the gravity and let the sheath bend with the gravity here, and then with a variable pressure we expected the sheath to go up, basically because of the force of the pressure increasing the force inside the sheath. So the sheath will go up and will decrease the curvature depending on, caused by the gravity in this case. So we have here like a clear curve, and as you can see, like the values are very close one to each other. And once we had both systems independently tested, we decided to perform some experiments with the fully system under some variable pressures. So as you can see, the curvature values are very close, and one of the things we were very, very happy about is that we could see some similar behaviors between the real system and the experiments, even on like specific pressure drop points in which the curvature of the real system was kept almost constant, and we could observe these behaviors in the simulations too, which was like really good for us, as we were combining two elements that we knew that they were working independently, but what we wanted is to see if we could model these interactions between this internal interaction between the sheath and the catheter. And as I see here, these two first experiments were thought to fine-tune the physical parameters. That first we based them on the real physical parameters of the system, but however we did some small adjustments to be as close as possible to our real system, so we could have this kind of experiments, this kind of results with the final whole system. Some other things, these are the interesting. So the last thing we wanted to see if we could model some interactions with the environment. So this is a small video of the growing of the sheath and the catheter. So as you can see, it's able to steer here and pass the first cylinder. Then when it approaches the second cylinder, we can rotate the whole system, the catheter, and steer on the opposite direction and pass the second cylinder from under. And not only that, but at the end, we can again rotate the whole system and try to get to the last cylinder, steering in the opposite direction again. So we can get this like a U shape at the end. And after all of this, we can retract the whole system with a negative velocity, and the system keeps quite stable during all the simulation, and taking into account the everything, it's quite good from our sides. Here is like a small summary of like different important points in which here is the growing, the steering in two different directions, and the contractions under a bit. So as you can see, the simulations are a bit long. So one of the things we should work towards is increasing the optimization of this simulation, as it takes a really long time to run at the moment. And other thing was, instead of using like the duct experiment, that was one of the experiments we used in the validation from the real system, we made these navigations through some model of the mammary duct we have. So we wanted the whole system to be enclosed inside the anatomy of the duct here. So we have here the growing a bit. So we want the catheter to be able to reach different positions inside the mammary duct. So here we wanted to go through this branch here under. So we steer the catheter, and once it steers and finds the proper geometry and is close to the wall of the mammary duct, we will continue navigating through it, and we will reach our end position.
You have 1 minute left, Mikel.
Okay, yeah. So yeah, more or less you can see here again the retraction. So you can grow the system, steer in any direction, and then retract the whole system once you reach your end position. Here the same. We have like a small summary here of different positions. So more or less like a small summary here of what we've been working on is like, from our knowledge, this is the first high-fidelity model of this type of robot. We have tested it in our proof of concept model, but we believe that it can be addressed, or it can be used to model similar systems. We have created the SOFA Python 3 package containing the necessary functions to add these type of systems to any custom sofa scene using like simple Python class functions calling. And the model demonstrates the effect of pressure in the curvature. As you see, the curvature decreases on pressure, so we know the stiffness of the whole system is dependent on the pressure that you are exerting inside the sheath. But we still have some problems that the simulations take currently very long, and if you run intensive hours, like if you run a lot of simulations one after the other, at the end you can and you change the parameters a lot, the systems start behaving in unexpected ways. So there are things we should look into and work a bit more. And for all these reasons, we don't think now this model is currently not suitable for real-time applications like teleoperations or control. So that's it. Thank you, everyone.
Thank you very much, Mikel. Is there any question in the crowd, like maybe a short question or at least one question? We exceeded a bit the time. I saw Etienne, I don't know if Etienne or Julien Ducrot, if you have, I mean, anyone from the soft robotics community. I just grabbed, I see Benjamin as well. If any one of you has a question, do not hesitate to unmute or you can even raise the hand. Now I'm actually checking if anyone is. And so what you mentioned at the end is that the model that you are presenting here is open source. I mean, you have some SOFA Python 3 repository available for including your robot into any SOFA simulation. Is that correct?
Mm-hmm. Yes. The thing is, right now the GitHub is private, but we hope we can open it soon. Yeah.
Okay, cool. Okay, cool. Definitely let us know about the link as soon as it is open. We could, and that's true for everyone. If you are having some plugins that you are developing or a project you'd like to highlight, we have, the name is far from perfect, but I mean, on the SOFA website, you have the so-called marketplace, and it's a place for highlighting any plugin or technology. So if you are interested in making your own work, highlight it there. Please do not hesitate. So thank you very much, Mikel, for the presentation. So you'll be in room 2 later on for questions. And we'll then move on directly. And I think we remain in KCL with Hadi, who should be there and ready to present. Hadi, yeah, perfect.
Yeah, hi. Can you hear
me? Can see you, hear you, and soon, I guess, see your screen as well. You should be able to share your screen.
Good. Yeah. Can you see my screen?
Loading, and yes, it's not full screen yet, but yeah.
Yeah, very good. And now that I made it in the presentation mode, do you see it?
Yeah, perfect. Thanks. The floor is yours. Go ahead, Hadi.
Very good. Thank you. Hi, everyone. Thank you for having us here. I'm going to present on behalf of an undergrad student, Katie Zhu at Erla, our work on finite element dynamics of the concentric tube robot motion and interaction with environment using a SOFA framework. We are based at RVIM Lab, King's College London, working on medical robots. Oops.
Yeah, we lost your presentation, but it's going to come back.
Okay, now it's back, right?
No, the screen sharing stopped, I guess.
Oh, what happened? I just, okay, sorry, I just hit enter and everything stopped.
Now it's loading again, yeah. Cool.
Okay, yeah.
We see your motivation.
Yes.
Great. Perfect.
You still have it, right? Okay, so a quick introduction. So concentric tube robots, as you see on the right, are catheter-like robots that can navigate anatomical lumens to reach surgical targets that are deep within the body. The motivation of this work is, well, CDRs have been extensively studied in quasi-static conditions, but dynamics of unique robot behaviors, such as hysteresis and snapping, and snapping means the rapid motion in the tubes. You may notice that in the video, like here. They are relatively underexplored. Novelty of this work is, for the first time, we present the usage of Timoshenko beam adaptive plugin of SOFA framework for finite element dynamic simulation of concentric tube robots and its interaction with deformable environment. Well, the plugin has been around for more than 10 years, but and the example seen of multiple catheter system for vascular intervention has been there, but no one really tried it for concentric tube robots, although they're really similar. We did it, basically we did it. But before that, I want to highlight our earlier research on reduced order dynamics of CDRs, and I'm going to say why at the end of this slide. So recently, we presented a CTR real-time dynamic model that captures both snapping and hysteresis based on a reduced order model with shape interpolation kinematics. This is how it works. So on the left, we have shape interpolated base kinematics of a multi-section continuum backbone. Here we have two concentric tube robots, two concentric tubes in this robot. Tube 1 is red, tube 2 is blue, and on the right you see Bishop's curvilinear frame that we presented. So we have a set of cubic spline that represents robot's overall backbone shape, regardless of the number of the tubes. As I said here, I have that for 2. And individual tubes define the integration range along the backbone curve. So I have a common curve, I have integration range that define each of the tubes. So I can define multiple tubes on the same curve. Interaction of the elasticity of these tubes decides the overall curve shape. Regarding the Bishop's frame, it comprises a frame tangent to the backbone curve, QF, followed by a correction to its rotation, Q5, to comply with the tube's special frame. Well, we noticed that, well, there is not a good publication on the SOFA Timoshenko beam plugin that represents the underlying physics, but looking into that, we noticed that, well, 10 years ago, they actually used something similar, using polynomials to represent the overall shape of each tube, and then updating the range of the nodes and adding nodes as the tube extends, or removing the nodes when they retract. But we noticed that they don't have a tangent frame representation as we have a Bishop frame. And this is actually the key to capture the unstable motion of concentric tube robots. What you're going to see that we couldn't capture with Timoshenko beam. So it kind of highlights the similarity of a work 10 years post the introduction of this Timoshenko beam, and we could publish it because, well, so far didn't publish the background theory of that, but how we can improve this plugin to incorporate instabilities in the system. Well, good news is we have our own modeling package as well. It's a MATLAB-based package for modeling soft robots based on reduced order modeling. I call it TMT-Dyne. You can have a look at my GitHub page for that. And we got that verified with our concentric tube robot experimental setup, as you see here. We have 2 tubes, actuation units, and magnetic tracking system for verification. You see the videos of different experiments that we did. These are simple experiments, multiple forward and backward rotation of the individual tubes. Something stopped. Yeah. In some of the videos, you see that we can capture the snapping. The videos are not synced, sorry for that. But it kind of shows how the things are. But these are the plots that we generate. Here in the 3D views, you see the experimental data with dotted lines, and the solid lines represent the simulation data. Good correlation between the results. Also, you see that in these time series. What I want, and you see that we have multiple instances of snapping during the motions of each of the tubes. And At the bottom, you see the error analysis, spikes of large error around snapping instances, but relatively small error afterward. So in our experimental studies, our modeling framework could maintain the state-of-the-art accuracy of 6% for stable motions and around 8% for unstable motions. So unstable motions around snapping instance. We could accurately predict post-snapping behavior, which is challenging for most quasi-static techniques. And you could successfully capture asymmetric motion during rotational return dynamic cycle due to system hysteresis by modeling material nonlinear damping. And by that, I mean, so if you see this part of the plot, this is actually a return cycle, rotating right-hand side, then rotating left-hand side, the same to you. But you see the motion is asymmetric, and this is because of the nature of a snapping in the system. Quasi-static models cannot capture this, but our model could effectively capture this. And well, the presented model has the potential for real-time control due to high computational efficiency and machine learning research as a simulator due to accurate dynamic simulations. But okay, enough about our early work. Let's jump into using SOFA Timoshenko beam plugin to model the concentric tube robot. So we wanted to model a realistic medical scenario involving deformable organ interactions. So we used Timoshenko beam adaptive plugin of SOFA framework, which, well, you know already about SOFA, and the simulation results are compared with our reduced order modeling techniques based on shape, interpolation, CTR dynamics. So as I said, Timoshenko beam adapter has been around for more than 10 years, mainly used for cardiovascular interventions. And the example seen has 3 catheter guide wire tubes that they can extend, retract, and interact with each other. And they can have a straight part and a curved part to represent the real geometry of a catheter and guide wire. Everything works in real time. It relies on a polynomial interpolation between the nodes to represent the kinematics of the system, and then well, the mechanics is handled via SOFA underlying mechanical solvers. So we basically tune the dimensions, curvatures, and stiffnesses and material density of the plugin, and could model our concentric tube robot. Again, it's strange that no one did this. The earliest work on dynamic modeling of CTRs is published in 2020, I think, and no one used SOFA Timoshenko beam plugin to model the dynamics of CTR in the years before that. Okay, so we got it tested. We could get interaction with the deformable tissue, and again we got it tested in comparison with our the same data set that we used for our reduced order modeling. Here are the results. Solid line blue is SOFA simulation results. Solid line yellow is the reduced order model. You see they're kind of correlate, but I want you to pay attention to bottom right. You see that we could capture the snapping with our reduced order model, but the SOFA model, the solid blue line, it actually represents a continuous snapping-free motion during the simulations. So what we observed is, well, of course, this is a preliminary study highlighting the limitations of this plugin to be improved later. We observed real-time performance of the developed model. However, the finite element simulation could not predict any snapping instances, despite consideration of the torsional deformation energy in the plugin and the small values for friction effect coefficients, Rayleigh stiffness, and mass damp. We conclude that presented scene is reliable for modeling stable motions of CTRs and its interaction with deformable environment. However, the plugin needs to be improved to correctly account for dynamics of an unstable system. our experimental study highlights the need for improving the plugin, and we hypothesized that if we could tune the material shear modulus alongside the material elasticity modulus, it could improve the results to some extent. And also, if we could implement a spline instead of a polynomial for representation of the tubes, and probably a bishop frame representation, the way that we did it with our reducer model, maybe the Timoshenko beam plugin could predict the instabilities in a system like this as well. Thank you for your attention, and yeah, happy to answer any questions. Yeah.
Thank you a lot for your presentation, Hadi. Is there any question in the crowd? Yeah, Christian, go ahead. I was going to poke you anyway. Go ahead.
Hello, Hadi.
Hi,
Thank
Christian.
you for your presentation. Very, very nice. Don't you think that the problem of so in the beam adapter plugin, when you have so as you said, it was more made for catheter navigation, and in fact, usually in catheter navigation, you don't have like two beams that are both curved in opposite way. So, but one of the issue for, I think, that prevent from capturing the snapping is probably that what we do is that we, in fact, the two beams. So if there are two instruments at the location where there are two elements, the two beams are adding their basically their stiffness to the same nodes. So we could, in fact, add correctly the bending, but not the torsion. So basically, in reality, particularly in concentric tube robots, the torsion between the two instruments are free, whereas in the plugin here, the two torsion are coupled. So don't you think it's that prevents to capture the snapping?
Yeah, I'm happy to hear that, because one of our suggestions is having access to the shear modulus to modulate the torsion independent from the bending elasticity. So yeah, I'm happy that our hypotheses, our understanding of the plugin were correct.
Yeah, so to my opinion, it comes from this issue probably.
Yeah. Yeah, good. We received this feedback as well, that we could use the Cosrod beam plugin, see if that one works or not. Probably that's
we are currently working on making the ability. So it's a work of Camille. The ability to have concentric instrument in general, so both for catheter navigation or for concentric robots based on the Cosra plugin. So it's a work in progress. So nothing to present today. Probably a presentation for maybe I don't know if you so maybe a presentation for next year. I don't know. So I don't know if you will present some stuff or not. Finally, Camille. I don't know if Camille is there.
No, Camille is not presenting. Yeah, thank you, Camille.
Yeah, but so probably next year.
But if you want, we can discuss this. Yeah, we can discuss this in the break rooms afterwards. If you
want. Yeah, nice to meet you, Camille.
Thanks a lot for the question and for the suggestion of discussion. We will end the session of today, of this morning. Sorry, this second session with the presentation of Paul. There is two polls, so I tried to poke one of you offline, but I did not know whether it was Paul Chaillou or Paul Chaillou that I was actually poking. Yeah, Paul, perfect. We see you now. You can share your screen. So Paul is working at INRIA, actually in the lab of Christian Durier that we just heard, and he's going to present us the reduced FE model that he's using for soft continuum robots. Yeah, we see your slide. Perfect. The floor is yours, Paul.
Okay, perfect. Is the sound good?
Perfect.
Okay, perfect. Hi, everyone. I'm Paul Chaillou from the first team, and I will present you today my PhD subject and how do I use SOFA during my PhD. So first of all, I will introduce you the SpiderMass technology, which my project is based on. The SpiderMass is a biological tool to analyze the surface of a tissue. It uses a laser beam that is bring up to the surface we want to scan thanks to an optic fiber, the red line on the skin. Then the laser hits the surface, it vaporizes few cells that are then vacuumed through a tube, the gray line of the skin, up to a mass spectrometer. Then, thanks to the data and to machine learning algorithm, we are able to discriminate the different kind of cell, for example, the normal, the necrosis, and the cancer one. But the SpiderMass is also able to distinguish a different kind of cancer cell, for example, from the type or the grade. So here there is a quick video of the SpiderMass. You can see here you can see the laser hitting the surface. It's a non-visible laser, so it's a post-port red line to make it clear. You can see the molecules that are vacuumed through the tube, and then they're going in the mass spectrometer for the analysis. The aim of my PhD is to design a new soft robot to do the same kind of analysis, but in vivo for mini-invasive surgery. We want to scan a surface point per point following a pattern in order to do a 3D image where we will display the cancer zone in a different color. It could be very useful because for cancer surgery, the surgeon have to make a very difficult choice, the choice of the security margin around the cancer zone. It takes like 2 or 3 centimeters around the cancer zone just to be sure he won't let any cancer cell left in the human body that may create a relapse or metastasis. And it's a difficult choice because the existing imaging systems are quite limited. It's only IRM or CT scan, and it's made a few days before the operation. And it's quite hard for the surgeon to know from this black and white image and to make the link between this black and white image and what it really see during the operation. But also because after ablation, the surgeon have to make an immunohistochemical analysis on the surface of the biopsy part in order to be sure I don't let any cancer cell left in the body. But these analyses are quite slow, 30 to 40 minutes, and are not that accurate. So our imaging system could be useful for 2 main stuff. The first one is to help the surgeon to know where is the cancer zone in order to design well the security margin. But also, he may use our imaging system to make an image of the walls of the holes in the human body directly to check directly in vivo if there is any cancer cell left. We choose to use a soft robot because as it's soft, it has a harmonious contact with the tissue and high dexterity. So this kind of robots are very well adapted for tiny and sensitive context as a mini-invasive surgery. But also, in order to do quick and accurate image, we want to follow an automatic pattern in vivo, and we hope that with the inherent safety of self-robot, we will be able to do so without any risk for the patient. So to design this robot, we are working with the University College of London. That is working on the new robotic module based on the European project STIFLOP. This module have a fiber around the pneumatic cavity to avoid the ballooning effect. Thanks to this fiber, this robotic module have very interesting properties in terms of bending and elongation. We may also put 2 robotic modules in serial in order to have a big workspace and even more dexterity. But the main problem with soft robots in simulation is that we have to make a complicated trade-off between the accuracy of the simulation and the computational speed. And so to improve this trade-off, we want to design a new modeling system. As the robotic module has a fiber, there are no ballooning effects. So the cross-section of the robotic module is static. So basically, our robotic module is behaving as a beam. And R is faster to compute beam than a full FEM model. It could be useful to compute our module as a beam. but it's a pneumatic actuated robot. So it's actuated thanks to pressure, and it's surfacic forces. So we have to find a way to make a link between surface forces and a linear model, a beam. To do so, we use what we call a mapping in SOFA that make the link between X that contain all the P point of the FEM model to the Q, the frame of the beam, thanks to a mapping that is represented here as the function A. So all the points of the FEM, all the P point, will be static in the barycentric referential that is computed thanks to an interpolation between the two beam frames. In this static referential, the position of all the P point of the FEM model will be static. So when the robot will elongate or bend, the FEM point will follow the beam. By this constraint, as the distance between the central beam in the module and all the FEM nodes are constant, it simulates the impact of the fiber that constrain lateral deformation. And so to project the forces, the pneumatic forces from the FEM space to the beam space, we use the principle of virtual work that says the work of the forces is the same in all referential. So the pneumatic forces F expressed in the FEM space is equivalent to the toe forces expressed in the beam space. So by using the Jacobian that we get thanks to mapping and the principle of virtual work, we get this third equation. With this equation, we may solve the equilibrium in forces in the beam space instead of the FEM space. It's very useful because, for example, for my simulation, the FEM model has 2,000 of nodes, and the beam has only 5 frames. Computing, solving the equilibrium of forces in the beam space instead of the FEM space is way more faster. You can see a small summary of the difference in terms of performances. I have made a full FEM scene in which I simulate the impact of the fiber with springs around the pneumatic cavity. And we can see that for one module simulation, our reduced model is about 5 times faster than the full FEM one. But we may also see that for a 2-module simulation, here the reduced model is 9 times, more or less 9 times faster than the full FEM node. It's due to the fact that for the full FEM simulation, main of the computational cost is spent to do the factorization of the K stiffness matrix that have cubic complexity. And in the reduced model, the most computational time is spent on the projection of the K matrix in the beam space that have a linear complexity. So more you will have elements on your model, more it will be valuable to use the reduced model instead of the full FEM one. And so now I have a real-time simulation in SOFA. Here you can see a video. I use the inverse problem resolution framework in SOFA to control my robot. You can see the orange dot here. This is the desired point for my robotic module. And I connected my SOFA simulation directly to the hardware. So all the pneumatic forces that are calculated in the simulation are applied in real time on the real hardware robot. So this way, I'm able to use my SOFA simulation as a control tool for my robotic devices. We submit all this work for RoboSoft 2023. So if you want to learn more, you can wait a few months to read the paper. I also drop my email in the chat, so feel free to contact me if you have any question, or you can also ask it now or in the breakout room. Thanks a lot for your attention.
What a timing, perfect. Even 20 seconds ahead, perfect, Paul. Is there any question in the audience? Either online, so I have the chat just under the nose I checked, there is no hand rising here. Nope. Is here. So do not hesitate to write it down or unmute yourself if you want to ask a question directly to Paul. In the room as well here, do not hesitate. I think so. I got the pleasure to see a bit in advance the session as well, the presentation as well. So, but from what I understood, basically there is a 3D model made of tetrahedra in which you have inside it a beam model, like a line model, and actually the forces are mapped onto it, which is basically just like using a beam model without using one. You are reprojecting all the 3D forces back to this line model. So instead of using a real line model and computing really the mechanical forces, internal, external forces on the beam, you're making that on 3D and then mapping them back onto these frames.
Yes.
I think, correct me if it's correct or not, Paul, but that's what I got. For the question, maybe it's could you maybe I did not catch that, but could you show us where actually are the pneumatic chambers? Actually, is that in the middle of the device, or is that in the six canals that?
I will just show my screen again. You can see there is a central lumen here in the robot to make all the, for example, the vacuum tube, the optic fiber to let pass all the tools, and the pneumatic cavity are around with this blue line, the fiber.
So that's the six different
Yes,
lines
exactly.
or other
Exactly.
chambers. Okay.
There are 6 chambers and 1 central lumen to let pass the tools.
Okay. And is there, I got another question, but I just check if there is no others, but was that targeting any specific like organ or surgery that, I mean, are you thinking about something specific to apply this kind of device or?
I think for the moment we don't selected any specific organs, but I think it can be adapted for all the organs are achievable in mini-invasive surgery. But I think for more especially for the ovarian or the liver.
Okay, cool. And as I already told you, but I mean that I would be really curious to see now the same simulation, but instead of using like one beam, but using the six ones as I think you plan to do later on, right?
Yes, exactly. It's ongoing work.
Cool. Any question? Yeah, go ahead.
Yeah. Hey, Paul, very interesting work. So a bit more about the braiding model. How can you change the angle of the braids and get the different behavior associated with it, like turning the system from an extensible actuation unit to a Mach-given one that shrinks?
So what do you mean by braid? Do you mean the fiber?
Yeah, the fiber, exactly. So the helical one, so assume you don't have a dense, the fiber, but you have it a more elongated one. So the pitch angle or the pitch angle would be much smaller, I mean, compared to that main axis.
Okay.
And then when you pressurize the system, it would collapse. It would shrink like a Mach-given muscle instead of extending. Do you think your framework can be used for modeling, general braided fiber reinforced pneumatic actuators?
Yes, I think it's a good question. Yes, for the moment, my model don't take in account the shrinking effect. And so it's a problem. It reduces my model accuracy. But taking in account the shrinking effect of the module will be needed to improve the accuracy of my simulation. If that was your question, right?
Yeah, kind of. Yeah, but we can definitely discuss more. No, I was actually more interested in how the fibers are modeled and if you can make them a less dense helix.
For my simulation method, I don't know if it could work with a less dense fiber because I just I don't for my reduced model I don't simulate the fiber itself. I just compute my model as a beam, and computing it as a beam take in account this fiber. Because well, for beam, the cross-section is static, and my fiber make my cross-section static. So computing my model as a beam, take in account this fiber naturally. So I don't know if it could work for less dense fiber, but from my opinion, it's not completely impossible. Yeah. Maybe you will have to adapt it to take in account the shrinking effect in order to be accurate.
Yeah.
Good.
We can definitely discuss more about this point.
Yes,
yeah,
with pleasure.
Interesting.
Thank you. Thanks a lot, Hadi. And we have here another question. François, go ahead.
Yeah, thank you very much for your work. Yeah, just maybe a very quick question about whether or not you drew some comparison between like an actual FEM model and your reduced model, and if you notice some differences, like in I don't know, very large deformations, or yeah, if you carried like this sort of comparison between the two.
Yeah. Yes, I have made a comparison between a full FEM and a reduced one, and I for the moment I haven't seen any difference between them in terms of accuracy. It was more or less the same. But yes, I know I really need to investigate this part more. This part more. I don't have made a very good experiment for the moment, but it's also ongoing work.
Yeah, okay, no problem. Thank you very much.
Thank you, Paul. Thank you, François. I'm gonna create right now the 4 breakout rooms so that everyone can go in a room. So I'm creating them right now. Perfect. And just before leaving the rooms, let me just share one last slide for the next step. So that were the presentations of this first session on soft robotics. So you'll find again, so it's Quentin in room number 1, Mikel in room number 2, Hadi in room number 3, and Paul in room number 4. You should all 4 get directly redirected to the proper room. If it's not, you can also do that manually. I can show you again, how to do that. It's just here, participant, breakout session, and you can join any room you'd like. So that's going to be a 20-minute discussion time again. And then we're going to have the lunch break, and we're going to restart at 1:15. So from now on, it's an hour and 15 minutes. We're going to restart with updates from the community, like the latest updates. There will be also some words about job open positions and stuff like that in the community. So do not hesitate to join us like in an hour. Back an hour in the main room, and over lunch there are going to be, obviously, as you can see on the slide, the vote, which is still open. I will send the link again in the chat. And there will be in the interface, the WebEx interface, a poll for, again, that will be reopened for your different usage of SOFA. So for now on, you should all be able then now to join any room you'd like. So to join Paul in room number 4. I don't have the slide anymore. So Hadi in number 3, Mikel in number 2, and Quentin in number 1. And see you then at least back in an hour and 15 minutes for the restart of this afternoon. Yes, Fred, you want to add something? There is no breakout session 1 anymore. Okay. Okay, I'll make sure it's working. Okay, thanks for the notice. I'll try to reopen one if necessary. Thank you. Camille, can you hear me? Yeah.
Yes.
Okay, sorry. Yeah, I was muted. Sorry for cutting everything so sharply. I could have let a bit longer for the rooms. You might see again. So that's for the rooms of right now. I'm gonna reopen them in a few seconds for people if you wanna chat again, and so you have some private room to chat. That's for lunch. Do not hesitate to just vote for your favorite open source contribution again. And yeah, and as I said, I will reopen right now the breakout rooms, and I think I'll try to do that without a timer. Okay, so that everyone can discuss limitless over the break. This is done. So I'll stay here. If you have any question in the main room and so on, do not hesitate. I'll still like have an eye and a ear on the rooms. Else, see you in 1 hour exactly to restart for this afternoon session with some updates about SOFA. And Quentin, I'll get back in the breakout room number 1. See you guys.